Good afternoon and welcome back. The next project on stage is NEWSAT. We welcome Gustavo Dias from UMinho, Nuno Correia from INEGI, Luís Fernando Velásquez Garcia from MIT, and our moderator for this session is Júlio Viana, Chief Technology Officer at Stratosphere.
Hello, good afternoon all. Thank you for being here, and I hope you enjoy this trip to the space here in Braga. Okay, so NEWSAT is a flagship project from the MIT Portugal program. I think they start in 2019, so it's almost 3 years and something. And basically, the goal of the project, we will see on the presentation, but just trying to summarize, is to use 3D printing or additive manufacturing techniques to build components, so let's say, so the building blocks of the new satellites, and in particular going to sensors, okay, and propulsion as well. So the base idea is to try to characterize in a quantitative manner the atmosphere, so the high atmosphere, the ionosphere, using onboard instrumentation. Okay, as was said, so this is a joint program between Stratosphere as the project leader, with the INESC, INEGI, and also the MIT. You already know the presence here, so typically Luís Velásquez Garcia is professor at MIT. He's a researcher of Microsystem Technology Lab. Okay, Nuno Correia is unit director of the composite unit at INEGI, and I also represent INESC here, well, in some way, okay, because he's from Porto as well. And Gustavo from University of Minho, but also CEO of the Stratosphere, and is the leader of the project, NEWSAT. So I will pass the word now to Luís, and then to Nuno, and then to Gustavo to present in the next 30 minutes the project, the results, okay?
Okay, thank you. Does everybody, can everybody hear me? Yeah. So good? Okay. I know we're pressed on time, but we would like to go over a handful of key results in our very ambitious program that, as you described, is about how can we make this space hardware better. So, of course, there are these constraints, like it has to be this, deployable, so they have this dispenser, they have to have certain dimensions, but you can do a lot of things inside the hardware, and that's where a lot of our work is centered. So we're going to talk about scientific instrumentation, propulsion, then a little bit about what one of my colleagues, Maria Young, from MIT in MECI, has done about this hybrid design and artificial intelligence, then move a little bit on what Wojtek Matusik, another colleague at MIT, has worked on metamaterials, and then we're going to hand over and hear what the trusts that have been led by Portugal have done, but this has been really a collaborative effort, and we're very proud of our results. So let's get started. And in terms of payload and systems that have been 3D printed, I would like to center your attention on mass spectrometers, plasma sensors, which are RPAs and Langmuir probes, and also propulsion. So propulsion is not something commonly found in CubeSats, but we think that it's important, for example, for the sake of disposing of the satellites, so to force it into re-entry and come out with a predictable way to get rid of the hardware, right? So let's get started. In terms of sensors, we have been developing a mass spectrometer. I'm not sure if you're familiar with the technology, but it's the gold standard for analytical chemistry. You want to know the composition of something, the quantitative composition of something. Well, you use a mass spectrometer. And it's, I thought it was well, there's a laser, but I can barely see it. So bear with me. In the upper left-hand corner is a schematic of one of these mass spectrometers. You need a charged mass in order to manipulate this mass with electromagnetic field. So perhaps you have an ionizer or perhaps there are ions already present, which is the case of the ionosphere. The ionosphere is plasma, so we don't need to use an ionosphere. But once you have these ions, then you can use all kinds of strategies to sort them out based on the mass per charge ratio, and then you can detect them, and with that we get your spectra. So what we did is to develop a mass spectrometer that is based on a quadrupole, which is a type of mass filter that uses RF signals, radio frequency signals, to filter. I think it's a very neat work because it's fully and monolithically 3D printed. So you see like at the center, at the top, those are the 3D printed quadrupoles. They're made in a polymer that's called PLA. The part that is like golden, it's the conductive part. So you can actually modify the PLA with nanoparticles to make it fairly conductive, of the order, I don't know, milliohm centimeter, very, very decent electrical conductivity. And then with that, you can make electrodes and all kinds of structures that exploit electromagnetic field phenomena. It's monolithic, so it doesn't require any assembly. So it just comes like that from the printer. So it's something that is compatible with in space manufacturing. So there are printers at the space station right now that could do something like this. And then we also did a lot of work in the electronics. Because maybe you have seen this presentation that you have like the gadget here is very tiny, but you have like a rack of instrumentation to run it. So that was not what happened. What happened is that we actually put together something that would comply with the limitations of a CubeSat in terms of power and in terms of the size. So it works at 265 megahertz. The screenshot at the top right is to show that these tiny electronics can actually deliver the voltage, which is hundreds of volts at 265 megahertz. It consumes, if I recall well, on the order of a fraction of a watt, like 0.8 watts or something. And this is an example of the kind of data you can get. So we can sample up to mass 300, but you only see one peak, which is the peak of argon, which is what we were looking for. So in the ionosphere, we're expecting gases like that, like argon, hydrogen, oxygen. So it has adequate range for what we want to see, and is something, again, that it would be fully disposable because the quadrupole is made of polymer. So when you go into reentry, it will just get destroyed by the reentry process, right? So let's shift gears and let's talk about a couple of sensors that we did for plasmas, for the ionosphere. So the first one is a retarding potential analyzer. It's a gridded device that basically is used to tell the ion energy distribution, but it can also be used as a mass spectrometer because if you are in space in an orbit, that means that you are at a certain velocity on the order of kilometers per second, 10 kilometers per second, something like that. And that's a relative velocity, so everything in that reference frame is to that velocity. So you're going to see shifts in energy based on the mass that you have. So if all the ions are moving at this relative velocity and they have different mass, then I should be able to pick it up by shifts in the energy with this device. So I think that's pretty neat because it's something that works with DC signals, but allows you to do the kind of things that you can do with RF signals, which is what I told you about with the mass spectrometer. So this device is, well, you cannot see it there, I'm afraid, but it's a fully digitally manufactured. It's using like our top technologies on commercial technologies, on ceramics, on metals, etc. But I think that thing is really important is that it works. What you see on the lower right-hand side is data that we actually got. And the long story short, these devices work as good, if not better, than the state-of-the-art of RPAs. But this is a very good proposition because they are very inexpensive to make, they can be made very quickly, and the bottom line is that they deliver. They actually can generate the data. So what you're seeing here is some IV characteristics, which is that the workforce for people that do electrical engineering, how to understand what's going on with the device. And what it's at the right-hand side is the process data showing what's the energy distribution. So this was done with a calibrated source, so we knew what to expect, and what we measured is what we were expecting. The second sensor that we made is a Langmuir probe, and if you have work on plasma, you know that Langmuir probes are really common sensors. They are basically electrodes that are biased at a certain voltage, and you collect a current, and based on the current and the voltage, you can figure out things if you make some assumptions, right? So there's some model behind, and But they are very robust, and they can cover a wide variety of parameters, and people like them. So we have our own version. It's also fully additively manufactured. We also developed the electronics to run it. I think it's also on the order of a fraction of a watt that it can consume. But it goes beyond that. It's a really neat work because we have this redundancy in the probe, so we can measure in real time with redundancy the parameters of the plasma. Let it be number density, electron density, the divide length, etc. So what you see here is this sensor run in control conditions, and you see how the estimates from the different combos of sensors that they work together. So we have a single Langmuir probe, a double Langmuir probe, a triple Langmuir probe, and they have different features. So, for example, if you do a triple Langmuir probe, it's the only embodiment that allows you to make measurements in real time, and maybe that's what you need. But perhaps you want to be particularly resilient to perturbations. So in that case, you want to use a double Langmuir probe because it's floating, and then it allows you to basically get rid of these perturbations to first order. But the important part is that. Sorry. The important part is that the measurements agree. And it just shows this strength about using software like generative design and using the latest technologies in 3D printing to make really compelling hardware. So let's continue. And let me talk a little bit about propulsion. So in this case, it's an electric engine, so it uses electromagnetic fields to accelerate the propellant, and that's something that is preferred in space because it's more mass efficient, so you can get more thrust per unit of flow rate of your propellant. So once you're in space, you have a number of options, and chemical propulsion is not necessarily the best alternative. So in this case, we use electric fields, and well, this is, again, a design that is monolithically 3D printed, where it has with a certain set of features that allows to take the propellant, distribute it, put it in the emission sites, and control it. But what is really, really exciting is what it does. What you can see is that it produces on the order of a fraction of a micronewton per tip. You can easily put thousands of these tips in a small area, in square centimeters. And what it emits is these pure ions. And what is related is that this engine has the highest ISP that you can get, so like a specific impulse that you can get for this kind of engines, and it's because the emission is monochromatic. And we believe that was enabled by 3D printing and these zinc oxide nanowires. Now let's shift gears and let's talk a little bit about other work done at MIT. The first one is led by Maria Young, and what she she looked into many things, but what I wanted to tell you today was about two key ideas. What she said is, okay, we have this excellent technology. How can we make to put it together? So meaning by that, designers, human designers that are well versed in designing and this thing called generative design. So generative design allows you to do things like what you see at the upper left, which, okay, you design something just by first principles, you get this, but you can certainly reduce a lot more the weight and perhaps be more effective if you use generative design, which is something related to artificial intelligence. So the first question that she wanted to address is whether the two things can coexist. Instead of like bumping heads, can you just guys work together? And the answer is that, yeah, you can if you divide the work. And by that I mean whatever that is quantitative, you can let the generative design do it. And the reason for that is that you can put quantitative inputs, and whatever is qualitative, so does it look good, is comfortable, is practical. Well, it's something more about having like the human touch and about having like the sensitivity for that, sensibility. So that was the first question that she successfully addressed. The second one is, what's the perception? It's a very different thing. Is the perception doesn't mean is what has actually happened, but it's what people think it happens. And what she got is a bunch of volunteers and asked, for a particular example of, okay, I'm going to make these bikes, and on the one hand, I have these engineers that are very well versed, and on the other hand, I have artificial intelligence. So under these metrics, which one you trust, which one does it better? And the consensus seems to be that people think that humans are better, except when there's when it deals with things like mass production or things that perhaps the human capability is not as, cannot put up with that. Like, okay, I want to generate a great number of designs of bikes. Perhaps that's something better suited for artificial intelligence. But I think another thing that is important, it was interesting in this study that Maria did, is that they found that the more you know, the more you have respect of artificial intelligence. So the older you are, perhaps the better you understand what it takes to put a successful design, and then you understand that it's not as easy. And if your degree of education, the more advanced is your education also, the more you respect the new tool. Let's shift gears and let's talk a little bit about metamaterials, but with no intention to steal thunder. We're going to talk about that later in this presentation. But all what I wanted to say is that Wojtek has been doing this amazing work on metamaterials. If you're not familiar about metamaterials, well, there are these mesoscale structures. So you have, at the micro scale, you have like the molecules, the atoms. Then at the macro scale, you have the object that you are designing. So these sit in the middle, and what they do is to tailor properties. Let it be optical properties, stiffness, density, etc. And that's what makes them so exciting, that it's like creating new materials without actually having to create the new atoms and the new molecules. So if you want to use metamaterials to find some optimal, you have to go through a lot of iterations and through a lot of possible seeds. So you see on the lower left-hand corner, there's all kinds of like unit cells that you could try. And perhaps there are far many more that you can imagine. So how do you go about that systematically? And what Wojtek and his team found is that they have, there is a way to describe them with graphs that is very efficient, that it banks on things like symmetry and similarity and mirroring certain structures. And with that, they have been able to show that the same structures can span a very wide range of properties, which is what you want, remember. So how does nature get the performance it has? Well, it does something similar to this. So it's everything made with carbon chains, but perhaps they're packed in a certain way to make them stiff and packed in a certain way so that they have these voids and perhaps can insulate better for sound or for temperature, etc. But it's basically the same molecules. So this is along the lines that I can use these cells and tune them so that I can span a wide range of physical properties. And with that, well, I'm going to give the microphone to Nuno, and let's hear what they did with metamaterials also and satellite testing.
Thank you. So I'll see if I can, you've seen my back. I see if I can do this without losing my mic. But you can hear me well, everyone, yeah? Okay, so let me just try to continue what Luis was saying with what some of the things we've been doing. So one of the things we were doing in Portugal was thinking of a way to package these instruments in an innovative way that continues from the trends in the project of looking into generative algorithms and additive manufacturing on every level of what we were doing, right? And in this case, we're looking at the structure itself. And I've got a small demonstrator here that we've done. And to do this, we were really looking into advanced materials. And we were really interested, and we did a PhD on this related to the project, on how we could use topology optimization to work with composite materials, with continuous fiber composite materials. This is still new today. It's still an emerging field. But it was something we were thinking of in 2019 or 2018 when we wrote the project. And certainly it allowed us to do some really interesting, get to some really interesting results. One of which was, for example, that the design, when compared to typical aluminum construction, we can save around 35% of the weight. The other thing, which is something you would expect in these types of structures, the other thing, we've developed materials to do exactly this. So there was a phase of the project where we were developing materials for this. And what we've been seeing, or 38%, what we've been seeing is that these technologies or these approaches allow us to do, let's say, approach design of a structure in a completely different way. We can certainly take new centers of mass and new masses of components of a satellite and use algorithms that would tell us how best to actually build these types of structures. One thing that I would like to just add to what Julio and Luis were saying is that, so as you can see, the satellite itself, or the NEWSAT, has had to make space for the thrusters that Luis was describing, for all the sensor payloads that go in the front. It has typical satellite elements to it. And these are quite heavy overall elements for a 6U satellite. And it's really interesting that we can achieve this design with this new manufacturing approach and being able to adapt to changing places of elements inside the satellite and creating new things. Before I move on to the next part of the presentation to Gustavo, I'd just like to say 2 or 3 things about INESC and their part of the work. So they had 2 elements. One of them had to do with IP, and to do an analysis of what was going on in the periphery of the project and understand if there was something we were doing that could be done, or that was being done somewhere else. But there was a really important part of what they were doing in terms of research that I think links back to why we were doing this in the first place, in a sense. So understanding these chemical species in the ionosphere tells us a lot about space weather. And that tells us a few things that we want to know about communications. So will satellites work well or not, depending on conditions like solar flares and things like that. It also can tell us something, we think, about formation of clouds and global albedo of the planet, and that has to do with global warming and things like that. So there is some information on how the ionosphere, what is the ionosphere and how it is in certain moments, but there isn't enough information today to actually get to our models and allow us to understand a little bit more how this influences what is happening in communications and weather, and how the functioning of the satellites can be done. This is something that I think is the continuation of what was being discussed. So there's a lot of work on how we can actually link the work that Matusic was doing in the MIT with actually manufacturing some of these elements and understanding the properties of what we can get. But I think, Gustavo, if you want to take the next stage.
Next stage. I can go from this side, probably. So this is what we have done in Stratosphere is what we call more digital part of the project, let's say. Okay, so one of the things that was developed during the project is what we call a digital twin of a satellite. We have developed several things that are related with the implementation of a digital twin of a satellite. The first thing that is important to understand is a digital twin of something needs something that will gather data on the spacecraft. So what type of data we can gather, things that come from the normal instrumentation that should be on the spacecraft, also from the payloads that we are installing, and also from the structural behavior, which was the first idea really, just to have a very good understanding of the status of the structure after launching and before and during deployment of the satellite. So there are things that are related what we put in the satellite and what we should communicate downstream to our ground control stations to be able to understand better the behavior of the satellite under certain conditions. 2 things just to be stressed. First, during and probably this is nothing new, but during an orbit, there are certain points on the orbit that we can download certain information. some information is more important than other, and normally the status and the health of the system probably is in the second layer of information that we transmit downstream. So we have to pick up what type of information we take from the satellite in each moment, and how we can reproduce the behavior of the satellite on the ground. So, saying that, passing to the ground part. In the ground part, there are something that gathers the data that comes from the satellite, and will integrate the data with certain specific tools that normally, when you are operating a satellite, you have. So the mission planning and scheduling, the integration with the operation and support tools. Also, you can correlate the status of the satellite with the flight dynamics of the satellite itself. There is a data management tool to be able to track all the information that comes for a long time of operation. And also, things more specific, tools that are more specific, focus on the SHM, which is the structural health management tool. Also, the energy system, how the energy system is behaving, and then an overview of the status of the satellite that will bring us information if the satellite is in condition to perform well the mission that was intended or not. So this is one of the implementations of the digital part that we have been done in Stratosphere during the project. Almost in the end, so be patient. Our way forward from this moment to the future. So we have a good collaboration with a program called CHESS. CHESS is a program from École Polytechnique de Lausanne, and they are also working with, this is not new, everyone is working with this, but they are working also with nanosatellites, with CubeSats. They have a 6U also solution, and they will launch in the first quarter of 2025. And our plan is to put flight models of the payloads, or at least one flight model of the payloads, piggybacking this satellite to be able to have flight hours of these solutions that we are developing here with MIT. So this is a way just to debugging any type of problem that can happen with these new payloads that we were developing during the project. So this is one of the actions that are being taken. And then we are preparing a new company, a new venture that is called Stratosphere Space Systems. We are actively raising capital, and probably if everything works well, we start the company next year, in the beginning of next year. And all the things that we are talking here will be developed within that new company and will be brought to the market. That's the plan of Stratosphere for the next 3 to 5 years, okay, in terms of this new venture. And that's it. Thank you for your patience. Thank you very much. Thank you very much.
Okay, thank And thank you to keep the time. So we are 1 or 2 minutes ahead. So I will start now the questions and answers. So I will program in this way. So I will start first putting some questions, and then I'll go to the audience. And if you have some question, please, we have a couple of minutes to think about the question you want to pose, and then we'll finish this session. So perhaps I'll start with Luis. So you were the first one, so you are not speaking for a long time. What is your general balance of this project? So in terms of the results that has been shown, how they are compared to the state of the art, and how they will allow to go to space, to go to monitoring Earth?
Yeah, no, I think that's a very, very important question, because a lot of people think that when you 3D print something, you have to make a compromise. But, for example, it costs less, but cannot do as well, or whatever. But what we have shown over and over in my group, and in particular in this project, is that there's no such a thing as a compromise, that if you choose the right technologies, you can put together hardware that is better than the state of the art, and then on top of that, it's very inexpensive to make. You can aggressively iterate it because it doesn't take forever to build, etc. So we're pleased to see that the different pieces of hardware that we put together for this project follow that trend. See, like by themselves. So like 3D print is like an afterthought. Okay, so this is like the best of its kind, and by the way, it was 3D printed. And that's very important for space because, as you know, putting mass in orbit is very expensive. I would say the best estimate these days, if you use one of Elon Musk's rockets, is, I don't know, $10,000 per kilogram, something like that. Yeah, but you need to buy a lot of kilograms because one of those rockets costs like 160 million. So it's expensive. So whatever you can do with reducing the weight, okay, that's one thing. But very importantly, if you were able to make your hardware from a multi-purpose feedstock. So the traditional way is that we have a stock of different plates and beams and screws and all different dimensions, and you need to have like this inventory, and then you put together something. But what if, like a plate, okay, this blob can become the beam, can become the screw, can become the solar cell. So I think that's what makes 3D printing for in space so powerful. Not only the part of reducing weight, but if you can print, if you can create it in space, I think it would greatly diminish the cost, and you can think of more things like repair. You don't need to send hardware, but you can perhaps just send the layouts and then get printed in space and be put together.
Okay, thank you. So when I was seeing the presentation, you present basically the most important results that you achieved, the scientific results, and perhaps for Gustavo, but there were other results than scientific. So let's say in terms of graduation, of qualification of human resources, new opportunities. We saw that there is a possibility of getting a new company, but besides that, new projects, for instance.
Well, there are during the project there was some master students and PhD students that they were exposed to this.
Yeah. Okay,
some of the more nitty-gritty work was done really during these PhDs, and probably Nuno can speak a little bit better about it. Of course, normally this type of technologies is quite emergent. We are blending a lot of things together. So we are blending digital technology like 3D printing that will enable in the future a new way to design the satellite and to produce the satellites, probably with also the right scale of launching and producing that satellites that makes sense to satellites. And this is quite interesting from the 3D perspective. And this clearly encloses and is related with these new metamaterials and also topology optimization and so on. So the idea also here, it was not here demonstrated, but one of the ideas is to include other features like PCB supports, supports for sensors and payload that can be produced during the 3D printing of the structure. So there is a lot of side knowledge that is not exactly here, but can be implemented on the future based on the knowledge of the project. Speaking a little bit about digital twinning. So we are one of the first to implement really a digital twin tool for a satellite. There is a lot of solutions for troubleshooting of problems. We are really trying to extend a little bit more to have an insight of the satellite based on a digital twin technology implementation. Of course, there is a lot of challenges here. One of the things is the communication of data is not fully tested. In what extent we can really reproduce the behavior of the satellite with the framework of data that we will receive. This is one of the things. But this is quite an interesting and result from the project that can be extended to other type of spacecraft and satellites. The baseline is already done.
No, you want to add some things about the qualification of human research?
Well, there were PhD students at the MIT. There were PhD students in Porto, in INEGI. There was work like that. We've taken students that had finished their engineering degrees, and they started work with us, and they've been pushed into a PhD on these topics. I think there's a lot of the work that's being done here that's really exciting. On the manufacturing side, what Gustavo was saying on, actually we were printing in 2D, as you can imagine. The setup there shows you that it was printed in 2D. We would really like to extend this capability to printing in these structures in 3D. With oriented fibers, this becomes even another problem. But certainly that's the way forward to further optimization of weight and support for internal structures. It leads to all these different problems in the mathematics of the topology optimization of this. But I think that the project allowed us to have these discussions, to interact and have visits from the MIT to Portugal, and students that came over and they were with us for a while. I think that was very valuable. The project also went through COVID, I think. We didn't mention this. That wasn't easy. I think it put a few things on hold. But I certainly think that it wouldn't have been, it's a really transdisciplinary project in the sense it incorporates a lot of electrical engineering research, it incorporates a lot of mechanical engineering research, and it blends the two in a very interesting way. I think it offers a really interesting opportunity for students to see how their bit integrates with everything else. Yep. So, yeah.
I think that was one interesting part of this project, because you have, and we have seen on the presentation, materials and materials manufacturing, 3D printing, PLA. We were discussing with PLA, nanomaterials. Then we go something to electronics, to sensors, and then we finished with digital twins. So we go from PLA to digital twins, and you can imagine this is really abroad. And I think that's the way of addressing this kind of projects. Okay, so I think in this sense it was a good.
I think this is just extending what Luis was saying. That's the additive manufacturing of this is what enabled the common line behind the whole idea. Yeah.
Okay, thank you. So you have a couple of minutes thinking in.
There's a question.
So that's why I'm opening now the questions to the audience. Please.
All right. I've been sitting here waiting. All right. So a lot of what you're focusing on is to use advanced manufacturing techniques, particularly additive manufacturing, whatever. How are you accounting for a coefficient of thermal expansion issues on those materials? Because a lot of those materials have pretty high CTEs. And, to do the prototype on the ground is one thing, okay, but you're going to fly it in space where you have thermal gradients in it. So how are you, and it seems like done correctly, the digital twin can enable that and you can design that in. But if you're using printing for precise instrument design, and the whole reason you're doing it is for that precision, how are you going to maintain that once you get to space?
Yeah, that one's for me. I think if we took the presentation originally, it was much more than what we were showing today. Some of the things we've done that we didn't show here are two important things to answer your question. The first one is we did a thermal vacuum test on the structure, and we're really looking into how this responds to the conditions in space. Even if the material here is not exactly what we would like to be using, there were limitations on having some equipment to do this. But we wanted to see how it reacts in space conditions, and we did that. We have a thermal vacuum chamber, so we could actually test this in space-like conditions. Yeah, we do. The second thing we did, and the reason why this is a continuous fiber 3D printed, is because the CTE in this case is controlled by the orientation of the fibers. So this would not be possible with short fibers, and this was one of the drivers of the project from the beginning. So it's exactly the problem we have. In the project, we developed our own materials for this. And the problem there that we had was that we were looking to buy machines that would print with our materials, and we could only find a machine that printed with standard materials. So the demonstrator we have here is a standard material, polyamide carbon fiber thing, but we had different materials that were developed in the project. Yeah.
Just about the digital twin. So in the
Thank you
digital
for the question.
Thank you. In a digital twin, we can follow up the thermal cycle of the orbiting. So you really can predict the distortion of the satellite in each point of the orbit. Okay, so this is also accounted for that.
No, I wanted to add two things from the point of view of the instrumentation. We did two things to address those issues of thermal expansion. The first one is choose well the materials. For example, our dielectrics are 3D printed, but it's a glass ceramic. It's not a polymer. So that's very important, because then you're going to have a lot better performance in vacuum, less expansion, and all that. And the second issue is that our designs actually introduce features to compensate for that. Remember that I was talking about an RPA that I just glanced very quickly, but these grids have these systems of springs that are distributed, are designed in such a way that if there is a thermal gradient, they actually change together, and they keep the collimation of the beam. So the idea is that these grids are transmitting these charged particles, and part of the reason why it works so well is because there is no interception. But it's thought that if there were issues in manufacturing or in thermal issues, they would actually change together and would result in still having a working device.
That was an interesting question, because all the materials that we have in the PLA, for instance, perhaps they are not, I will say, prepared for space conditions. So it's not only the thermals, but also cosmic rays, other type of aggression, let's say, to the materials that they have to withstand. And I think this project has this advantage that when we talk about 3D printing, we thought about normal materials. We can go a little further and go for composites or continuous fiber composites, putting more pressure, let's say, on technology, on additive manufacturing. But here we are also putting, through the materials, the need of special materials to put some requirements to the technology. So we are developing also the 3D, at least putting some requirements on new 3D printings for space materials, let's call it this way. Now, we have time for a couple of questions, so if there is any other question from the audience, please.
First of all, congratulations on the presentation. I have a question regarding a specific part that you've showed on your presentation. There is, I'm not sure which part it was, but it had many very small holes in it. And my question would be if it was challenging to print it, what challenges there were, if so, and if not, what would be the smallest pore size that you could get before the appearance of defects?
To me?
To anyone.
No, so it was something that I showed?
Yes.
Oh, okay. Yeah, I think it was an RPA. But
This one?
No.
Yes.
Next.
No, I think it's that one with
This
those
feature?
pores.
The
Oh,
size,
those have
Or is the one before?
before.
That one with the holes.
Or that one?
No, the
dimensions.
first one.
Oh, the first one. Oh,
No,
okay. No, yeah, that's
Trust
That
right?
one, that one.
Yeah, because you have the coins.
yeah. So
It's all very fine
So
detail,
that's made in stainless steel, and it's using a printing technology that is called binder jetting. So it's the difference is that mainstream metal printing is based in powders and laser, and it has these issues of there are these thermal hysteresis, and it translates into introducing these stresses and making things bold. So it's a lot harder. So in this case, you decouple the printing from the solidification, and that's why to first order it takes care of all those things. So all that long story is to say that it allows you to really print based on the voxels, and the voxels of that technology are on the order of 30 microns in plane and 30 microns of height, the slicing. So those holes are what you can print consistently that is small enough, see? And I believe that's on the order of 200 microns, see, without any kind of treatment. Those holes, if you are talking about the holes that are at the bottom, which connect the reservoir to the tips, those are the 200 micron holes. And what they do is they serve like a wick, like for a candle. So they transport the liquid by surface tension, and then they spread out. And then the liquid climbs, the tips, because there is this forest that is made of zinc oxide nanowires. And if you're talking about the holes of the apertures, well, that goes a different consideration is, can you generate electric fields high enough to trigger the electrohydrodynamic phenomenon? And it's also related to the positioning, because what you would like is what is called achromatic lenses, which is that you don't introduce this off-target firing of the beam. And long story short, that's on the order of hundreds of microns, let's say 500, 600 microns. But it's because it's related to other considerations that is not really the manufacturing. So it goes beyond that. It's about how repeatable and symmetric is the electric field that you're going to generate at the tip.
Thank you.
Okay. So thank you. I have here the time is blinking. That means that we are one and a minute off behind the schedule. So I would like to thank all the presenters and thank you for listening.